Nice to see you further in the afternoon. Welcome again. I have the pleasure to introduce Shanshan Wang, who's a full professor in the Department of Management Science and Engineering in Beihang University. She's also a member of the great family of GERAD. She was also a postdoc at HEC Montréal. She also did a postdoc at the Chinese University of Hong Kong. Her research mainly focuses on distributionally robust optimization and decomposition scheme for large-scale mixed integer linear programming. And her research was showcased in the top-tier journals such as Operations Research, International Informed Journal on Computing, and European Journal of Operational Research. Thank you. Also, it's a great pleasure and honor to have you visit and present your work since you've left Montreal.
Thank you. Thank you for Eric's introduction. And I also was a postdoc of Eric, and it's my very honor to work with Eric and have a lot of good memory here. So it's very excited to come back and visit again and maybe do a talk in GERAD. This is my first talk in here. So yeah, so just enjoy it. Today I will share my recent work named the Joint Inventory and Routing for the EV Battery Swapping Network with Hybrid Charging. This is a joint work with Wang from Washington University, Yongwei from Lanzhou University, and Lili from BIT. So this is the outline of my talk. First, we will go the motivation and the problem description. So as we can see with the pictures, a rapid growth in the EV market over the last few years. So we kind of witnessing a transformation of the transport. This is especially in China. So in China, China's annual production and sales exceed 12 millions with more than 40 market shares. And the chair's sales make up more than 15% of global market in 2024. But there is a hidden crisis because it takes too much pressure on our power grids. Our power grid was not built for this stuff. So many people are sick from the new charging model to shift the power pressure. So now this charging and swapping are two popular charging models in China. The first one is a charging model, but the charging model has some problem. You need to wait maybe until maybe half hours to hours to fully charge. This is really waste time. And you also, if you know the battery is decreasing rapidly. So if you own a battery, it's kind of your own decreasing asset. So and the other problem is like it's inconvenience, it's unsafety, and also some other problems. But for the swapping models, it is shifting. It maybe only take 20 seconds to switch the battery, then you can go. So this is very fast than this charging model, and it saves the space. You don't need a lot of space to parking your car. You can use the less space to get the same service levels. And it's also safety because the battery are collected and charging in a controlled environment. So this is more safety. This kind of battery is not a product to you, it's a service to you. So this is the benefits of the swapping model. Consider this benefits of this swapping model. They propose a project Optimal Surprise, which is a collaboration of three very big industrial companies. Like the first one is the one of top China EV maker company. And the second one is leading in the building the swapping station service. And the third one is the electrical techniques companies. With this object tool, the main goal of this object is want to build a massive and like a standard swapping stations, and to show to the people that the swapping station is just as fast as and reliable as the gassing traditional gassing station. And by 2025 June, New has built more than 3,000 swapping stations, and Autumn has built more than 800 swapping stations. But there are also some more problems for this swapping station. Like the main problem is the mismatching between the transportation and the power grid. As you can see, this is a map of Beijing in China. So this is the downtown, and the demand in the downtown is very high. During the demand peak, maybe the swapping station will suffer some more congestion and user quitting. But at the meantime, this is the great the power grid of the Beijing. You can see the downtown's power capacity is lower than the suburbs. So that is a kind of mismatching between this one and this one. So for some companies like Beihang, green energies, they kind of like, oh, this has a much capacity, so I built a centralized charging station in this supplies, and I collect this all the battery from this and transport to this to the supplies to charging. And after they use some more wind farm or the photovoltaic station, like this renewable energy to fully charge, then they will give this fully charged battery back to this downtown area for the battery service. Yeah, because that is the power grid, the kind of the feature of the power grid. Yeah, because yeah,
a lot of demand.
yeah, you also demand so the you use a lot of power in this downtown part, so the capacity is less than the suburbs, and also this suburbs they can build like wind farm and a lot of renewable energy, for the high for the faster charge. So the battery charging in this area is faster than this area. Yeah. So this is the benefits of the centralized charging station. So we consider about these three model charging. One is on-site charging, it's just charging on the swapping stations, and you can use the battery. So each swapping station is independently handle the charging and the swapping. The benefit is there is no transport cost and no leading time, because you need the truck to collect all this battery, and then you need deliver this battery to this. So it has more leading time. And there is also long on-site charging, because the power grid feature in the long charging time. And the second is you need high battery inventory, because charging is very low. You need a high inventory to satisfy all the demand. And the second one is centralized charging. Centralized charging is you can charging at the centralized charging station and swapping and just swapping as a swapping station. It's like the swapping station didn't do any charging at all. So just give the battery to the centralized charging station, and let this centralized charging station to charge all the battery. So, and we started this hybrid charging. we want some on-site charging for the high SOC battery. So this is because if you have a high SOC battery, maybe it's very far to charge. So it's don't use it doesn't need to transport all along to the suburbs. And centralized charging for the low SOC ones. The benefit you have a shorter charging time and low battery inventory, but it also has some conflict operations to balance inventory and transportation cost. You need to balance this one. This is our problem. We to study this hybrid inventory and routing problem, we model this like this one. We have the central charging stations, we have swapping stations. Swapping station can also have some charging, and this track is like go route from this central charging and pick up and deliver the battery, the swapping station asked, and also load the empty battery back to the charging station like this. And we consider several uncertainties. First, the demand is uncertainty. Second, the charging time is uncertainty. We consider our objective is to minimize the transportation cost and the battery cost. Our decision is to find the initial inventory for this charging station and for the swapping stations, and also for the optimal routing for this track.
The swapping station use batteries that are half full to charge the other batteries that are half full before, so that the trucks always carry empty batteries, or is there a way of not transporting half full battery back to the charging station?
No.
No.
Yeah.
Here we
Because
talk about like smart grid, where cars could be used to power the grid with their battery, so that if you have a half full battery, you could use it to provide electricity to the grid, and then perhaps this electricity to charge another battery, so that you make sure you don't carry batteries that contains charge. I mean, so it would be more efficient, but here there's no such other. It's just a feature of the problem formulation.
So that's reflected by the pump, it always empty battery. No, you both empty and fully charged.
Yeah, for this car, the
There's
same
some
car.
cases that the half charge batteries.
Because this is the taxi, maybe the car coming into this swapping station wants to the full charge the batteries. So if it has a high SOC battery, maybe it can that's charging on site, that's charging on this swapping station. But if it has a very low SOC battery, maybe and back to this charging station. So we want this all be fully charged for all the
But it could be 15% state of charge and be sent back to the charging station instead of emptying the battery. Maybe do something like and then moving it empty. Right?
Yeah.
You do carry back some batteries that are not fully discharged.
Yeah.
How much time does it take to discharge a battery?
How much time?
You don't just want to waste energy. But anyway, it can be all adaptive anyway. Some all of it. Interesting.
So I will want. And we also have assumptions for the demand. We assume it follows from a stately independent increment process with some given mean and variance at each swarming stations. And for the charging time, we also assume it follows discrete charging time, like for the charging time on-site is with probability PO with random charging time O, and for the centralized is similar like PC with the discrete charging time with TC. And here is I think is a journey of a battery. How what's the maybe when like empty, I just use empty battery because this battery needs to be charged. So I use the empty battery to call this kind of batteries. So all this battery coming to the swap because this is the demand for the battery. So this is number of the empty battery coming into this swapping station with the probability PO, they will charging on-site, and with probability PC, it will transport to the charging station, and with this random charging on the charging stations. After that, they are fully charged, then they can go back for the service, and we model this two systems, charging system as a continuous systems. We use the infinity servers. That means all the batteries doesn't need to wait. Like if empty battery come to the on-site station or come into the centralized charging station, they can charge directly, so no need to wait. And we also use period time t. This means at for each end of this time t, I will send a truck from the central charging station to all the swapping station. I will deliver the required battery from the swapping station and pick up the same quality of empty battery to the truck, and then back to the charging stations. And this round trip delivery time is denoted at top. And we need to decide the initial inventory SI and the initial inventory at this charging station. We use the order up to policy, which means once we decide this initial inventory, and at the end of this period time t, and I will say, oh, how many fully charged battery I have now, and this is the pre inventory target, like SI. I need to request this difference between what I have and what I need. So this is the order up to policy. So this is the number I need to ask the charging station deliver me the fully charged battery. So from the charging station viewpoint, we can say, oh, at any time t, each swapping station has a demand ICT. Like at the end of this time t, they will ask me to deliver the fully charged battery to each of this swapping station. And then after this talk, that is a round trip for this truck. So the truck will bring back the empty battery to me, and I will charging the battery with a random charging time the top. So this is the operations of the charging station. What the main results of our paper? We decide the initial inventory for this swapping station and the charging station. We find the optimal routing, and we reformulate it as a mixed integer second order conical reformulations, but this is very hard to solve. We propose a submodular based valid equality, and we use the branch card to solve it efficiently. Finally, we use a case study to find some insight from this whole system. Here are some related literatures. I think the most related is Xi et al. 2023 MS paper. This paper is having the centralized charging models. So we extend this model to kind of battery hybrid charging systems. We can use on-site charging and centralized charging. We get some more close-formed analysis. We develop exact algorithm for this hard solved problem. Yeah. So let's go to the main model. The main model, this is all the journey of this system, and we identify the non-Poisson swap demand, because in the before we assume the demand is sustainable, independent increment is a general process, is more general than the Poisson process, because we identified from the real data that the demand is not generally follows from a Poisson process, and we analyze the operations of a warming station and operations of a charging station. This is a real data from Beijing in 2019 December. And this is a figure for the hourly demand. As we can see, is the demand peak disappear in the morning and in the afternoon. And we use the stochastic test to find for each time period at the 1 hour time period the number of non-Poisson days. So generally, the demand is not exactly a Poisson process, so it uses a more generally process to account this demand uncertainty. Before analysis, the operation of a swarming station and the charging station that need to identify the inventory, initial inventory. I first give some more notations here, like we talked before. This is the at any time T and the swarming station I. This is the demand of a battery. With the probability PO, it will come to the on-site charging, and with probability PC, it will go to the centralized charging. And for this on-site charging is also follow a discrete charging distribution. And for this one, for each allo battery type of battery allo in this on-site charging, the number of the demand is this one. And we assume this we can get this one follows multi-nomial distributor. And similar for the number of the empty battery, like a charging with the charging. This one is with the charging time delta C1. So it's kind of this. For the swarming station, we want to decide the optimal order up to a service the level as such that the stored out probability is no greater than this epsilon, and we need to identify this one. This one is the battery deficit. So the battery deficit larger than this inventory is probability is no larger than this epsilon. And what's this the deficit of the battery in this swarming station? It means the number of battery that is empty and minus the number of battery that is fully charged. So this deficit is caused by the on-site charging and the centralized charging. Because if once this empty battery enter this swarming station, it can be charging on site and charging on the central stations. If the battery is at any time if the battery is not fully charged, then it will cause the on-site deficit of the battery. If the battery is not what I asked the central the charging station the number of battery and what the central station delivery to me is has a gap. So this is caused by the deficit is caused by the central station, the charging station. So this have two elements. This is caused by the battery defect caused by the central station and caused by the on-site station. For the on-site battery deficit is equal to this one. So which means if the battery at any time t, if the battery is not fully charged, then it will cause the battery deficit. And for the charging station cost deficit is equal to this one. Means this is the number that I will send to the centralized charging station to fully charge that, and this is the number that is at this time the centralized charging station gave its fully charged battery to me. So this is difference that is caused the battery deficit. Here is the example, and if this is the t is the period time t, and this is tau is the truck come to this swarming station. And if this t is less than if this t is less than this number, which means no car has pick up the fully charged battery to me. So the deficit is this number. And it's this number from 0 to current time to current time. And if this t is larger than t plus tau, means a truck has delivered this number of fully charged battery to me. And then the deficit caused by this charging station is equal to from this one to this one. This is if this is t. So once we understand this, then it make the problem very simple. We can just replace this with this one, and we can, because this follows multiple normal distribution, we can get some more mean, and we can get some more mean and variance value and some covariance here. Finally, we can get the expected of the design of the definite battery, the number of definite batteries. And the first part is the deficit battery caused by the centralized charging, and the second part is caused by the on-site charging. You can see the first part like this. the effect of the deficit battery is increasing until a car is here and give me some fully charged batteries, then the deficit is decreased. Then it will increase in medium, and another truck is here and it will increase like this model of the deficit of the battery. And for this on-site charging is like at the first time we need to charging the battery on-site. After fully charged, the deficit will decrease a little bit, and then after all this battery after all the charging maximum charging time, then it will go to the average. So we can also get the variance of this deficit, the number of deficit batteries. After we have the mean and the variance of the deficit of the number of batteries, we assume this the number of deficit batteries follows normal distribution. So we can directly reformulate the transcontinent as this form, and we want the initial inventory is the soup of this number. So means at any time we can get the maximum of the inventory level. And then we can reformulate this at this part. But we found that this is non-convex and non-convex. Means this T plus VV is also our series, relative series to get the dual time. So this is also hard to solve. For the operations of the charging station is similar to the swapping station. We also need to find the deficit number for battery for this charging station, and this is larger than the initial inventory. Probability is less than a small number. And for this charging station, this is kind of some of this deficit from this all swapping station. So what causes the charging station deficit batteries is only because the transportation, and because the transportation is in the car, so truck is not come here yet, and I also need time to charging all these batteries. So it's caused by this transport and this charging time. So this is simpler than the swapping station. So at any because for the swapping station, the demand will come anytime, but for the charging station, it will always come because it's only come at the time t, because at each time t I will send a truck, at each time t I will send a truck, and the swapping station will ask me some for batteries, I will send a truck. So it only occur in this t, and so we only focus on this kt. Kt is the integer, is an integer value, and at any time kt, we want to see how many batteries are not fully charged. So we can compute this number to get the deficit of the batteries. So similar, we can compute the the mean and the variance. We can get finally we can get this initial inventory value for the charging stations. So this have some parameter that is dependent on the decision top. So this is the track from the trip time. And for the routing decision is much simpler because it's just some classical constraints on the routing, and we can define some more decisions like this as AI is the routing decisions, and the round trip delivery time tau is like from the charging station and the back charging station's time delivery time tau, and the delivery lead time to each swapping station is Vi. So this is the final reformulation of our problem. The last two constraints are as complex. But luckily we found for this alpha, beta, gamma depends on this top is a piecewise constant function. So we can define the binary variable to see which tau follow into the which interval. Then we can reformulate this one as a constant. So the hard one is this non-convex and non-concave constraint. This constraint can also be reformulated as OP constraint, but we found it's very hard to solve. So next we develop some improved card. For this constraint, for convenience, we just define the function G as this constraint. We found this constraint is a submodular function, which means if we have a small set and a bigger set, if we add item to a small size, the marginal value is larger than add to the larger set. There are some exciting valid equality for these submodular functions. This is the general procedure to generate the valid equality. Like given S bar, we can solve it in decreasing order. So based on this order, we can calculate the marginal value for each item. Then we can get this valid equality. But we found not just this function. We also have the bound on this X. So we want to use this bound to generate input valid equalities. Similar like that, because before we just wanted to we didn't see this bound, we just wanted to add one item to calculate the marginal value, and another item and calculate the marginal value. But if we have this bound, we found it's the number of we add in the number of items we add into the set is generally bound by this one. So we use this one to get a better value for each item for xi. But these two equalities are not facet defining equalities. So we want to find a better one. So next we try to find a facet defining valid equalities. We generate the facet defining equality like this. We first also sort it in decreasing orders, and we found a max. No, not small is the biggest. I think the identifier such as such as the sum of Pi from 1 to k is less than b, but if we increase this k, then it will larger than b. And for the item from 0 to k, we can use the same one from the traditional valid equality, but from the Q1 to M, we solve this lifting coefficient problem, and we can improve this is the facet defining for this for this constraint, but for this set of constraint, but we found that this one is very hard to solve because this is also a binary integer problem. So we relax the integer and we solve this reduction problem and we get some closed form solution of this reduction problem. So that will be very fast to generate the valid inequality. For the case study, we use the real data from Beijing to do all this study. First, we show the computational results of all this proposed algorithm. This one is the proposed algorithm, the valid card, and this one is the user bound as improved valid card, and this one is the traditional one, and this is simplex. And the T is for the solution time, the time for generating card, the improvement time over this simplex, the number of cardinals iterations, and the number of solved instances. And we found our proposed valid equality can be very faster than the have the better performance than other problems. Especially when compared with this one, it will improve over 15% for this solution time, and compared with this one is kind of over 18%. And for this simplex, it cannot solve all the instances. For some instance, it can only solve maybe 7 to 8 instances, and for the SL instance, it also leave a larger gap here. So this table shows the efficiency of the proposed valid equalities, and we also consider different number of swarming stations, and also show this the proposed algorithm valid card can perform best over the other methods. And for some insights, for this figure, we varies the onset probability from 0 to 1. 0 means the probability of onset is 0, so the battery will all charged on the charging station, and 1 means they will be all the onset charging. And we found this is the optimal period time based on the different probability PO. And we found when PO is equal to 0.4, it achieves the lowest cost. And is kind of reduce the cost by 3% with one time period 1.5 hours. So we fixed the PO equal to 0.1 and the T equal to the 1.5 hours, and we varies the demand scales. This is the demand scales is increasing, and SSCS means the total inventory of charging swarming station and charging station, and this is the inventory of the charging station, and this is the inventory of the swarming station, and this is sum of this one. And once we can see from this figure as the EV demand scale increasing, the inventory, the total inventory is kind of linear with as this demand scale with respect this demand stream, and always this hybrid charging model give our the lowest total cost. And similar for this various scales effect, they also increase the variance of the demand. And we can see some similar results here. Here is the charging time ratio varies, which means for this 4, it means the onset charging is very fast, and for this 7 means the onset charging is the charging station is charging very fast, so it's kind of makes sense. Once the onset charging is very fast, then the optimal, so we will charge all the battery on site. Otherwise, we will charge all this on the centralized charging stations. And once increase this on-site charging speed can efficiently lower the total battery inventory level. So this one is it also varies the distance between the warming station and the charging station. So as the distance increases, the charging model is also changing. Like from if they are very close, so the charging station is very close to all the swapping station, we will prefer the centralized charging. And when they are very far, so that is maybe cost a lot of time to transport these batteries. So then the on-site charging is better. To summary, we study a joint inventory and routing optimization.